In this video I want to try and do a fairly quick job of reviewing a whole lot of subject matter on vectors. So there's a lot to get through, and so the video might go a little bit longer, but everything that I cover in this video will be stuff that we've considered before. I think there's a really good opportunity now to review some of this stuff which in Unit 1 some of you probably didn't quite consolidate, and so hopefully we can do that now. So remember, a vector is a quantity that has both magnitude and direction. So one of the sort of fairly obvious ways of representing a vector would be to actually draw a line segment, a directed line segment. And we could think of that as joining 2 points. Let's call them A and B. And so we could have a vector from point A to point B. Now we might give that a name, and when we're using sort of handwritten notation, we'd use a lowercase letter and put a little tilde underneath that to indicate that it's a quantity which has not only a size but also a direction. So we can see in this case here that this vector from A to B could be represented by saying, what's that, 6 units in the horizontal direction, 2 units in a vertical direction, but 6 units to the right horizontally, and 2 units down vertically. And so there's a couple of ways that I could represent that. I could say vector u. Well, firstly I should, in terms of notation, indicate that I could represent the notation either as lowercase u with a tilde or as AB with the directed arrow above it. And then I could represent that using a column vector. So say, well, it's 6 units in the positive horizontal direction and 2 units in the negative vertical direction. But I could also use component form, where I actually use the idea of unit vectors in the positive or in the horizontal and vertical direction. So let me just indicate over here, remember that I would mean a vector of magnitude 1, or unit vector, in the positive horizontal direction, and j would be a unit vector or vector of magnitude 1 in the positive vertical direction. So if we define I and j in that way, then we can also express all of our two-dimensional vectors in component form in that way. We could also then talk about the magnitude of u. So if I had a vector u or a vector AB which was defined in this form, then by Pythagoras' theorem I could say that the magnitude of this vector would just be the square root of the sum of the squares of the sides. So what's that, 36 and 4 root 40, or I guess I could express that 4 times 10, so it's that 2 root 10. Would be the magnitude of that vector there. Now that probably lends itself to a reminder of the other way that we could express a vector. So let's generalize this a little bit and remind ourselves of polar form and its relationship to component form. So I'll generalize a little bit and say, let's say I have a vector which is of that magnitude in that direction. Now there's 2 different ways that I could express a vector quantity. One would be to say, okay, it's got a magnitude of, let's say, r. Let's call this vector u as well. It's got a magnitude of r, and it makes a direction of theta with the positive horizontal direction. If we were talking bearings, that might be, an angle with east, I guess, in the positive horizontal direction. So I could express it as having a magnitude of r and a direction of theta, where theta is the angle with the positive horizontal. But I could also express this as having components of x in the horizontal direction and y in the vertical direction, where those are perpendicular to each other. So polar form would be to write u equals r comma theta there. So polar form is to give a magnitude and a direction. And if I wanted to convert between polar form and component form, so that would be what, xi plus yj. if I wanted to convert between those two, or in that particular direction there, so from polar form to component form, then I could simply do so by saying x is going to be equal to r times cos theta, and y is going to be equal to r times sine theta. Now remember, theta is an angle with the positive horizontal, so it doesn't have to be an acute angle. It could be an obtuse angle, it could be a reflex angle. Likewise, we could measure in a positive or a negative direction. Now in all of those cases, using this here, r times cos theta and r times sine theta, would give us the correct, the correct expression for x and for y. So it's pretty straightforward. When we convert the other way, life is not necessarily quite as straightforward. So if I wanted to go from the form u is equal to xi plus yj, and I wanted to convert that into polar form, comma theta, then I could first of all get the magnitude. Well, r is just equal to the magnitude of u, so that's going to be, so in two-dimensional form there, just the square root of x squared plus y squared. And theta, well, tan theta would be equal to, so tan theta would be equal to opposite over adjacent, wouldn't it? So looking in that triangle there, I'm saying the tan of theta is equal to the opposite side over the adjacent. Now that's true, but we do have to be a little bit careful, and you might remember getting caught out sometimes with not getting the right angle, and that's because tan is positive in two quadrants and negative in two quadrants. If we're sort of considering theta as an angle between 0 and 360, then we'll need to be a little bit careful about just making sure our y and our x are expressed in a way that we get the right angle. So I'll do an example of that sort of when I get to the end of this video, because I think that's probably something that we need to remember there. Now what about position vectors? So when we're dealing with vectors in a geometrical sense, because remember, vectors could be expressing just acceleration or velocity or force or something like that, and in that sense they're not really geometrical vectors. They're kind of imaginary directed line segments then, aren't they, that are just representing, the speed of something in a certain direction. But if we're actually talking about the position of points in space, so if we do have, a point A here and another point B down here, and we're trying to express a vector joining those 2 points, so let's say there's a vector from A to B. Now if those are 2 points in space relative to some origin, some point of reference here, so I can say, okay, there's a vector from O to each of those. So I'll call this the vector A and this the vector B. So let's say A is the position vector of point A, and vector B is the position vector of point B. Then it follows that the vector from A to B, well, if I was to sort of use some vector addition here, I could say that's the vector from A to O plus the vector from O to B. So in other words, I'm saying the vector path from A to B is the same as going vector AO plus vector OB, and that is going to be the negative of A, let's put in equals there, equals negative A plus B. So can we see that there? That's the negative of vector A, or heading along A in the opposite direction, plus the vector B, and so I'd typically say, therefore, vector AB is always equal to position vector of point B minus position vector of point A. Now, that's not on your formula sheet, but it is one that's incredibly handy to remember. Right, let's extend to the idea of 3 dimensions, and then we'll consider a couple of other results. Now, we'll spend some more time on 3D vectors in the next video and in the next section, and particularly thinking about polar form. But let's try and sketch for ourselves a vector that's in 3 dimensions. So to do that, we need to represent a third axis. So let's say there's our x direction, our y direction. So if you can kind of picture that, that's sort of a horizontal plane that those are lying in, and then this one here will be our z axis. So I'm going to pick a point which lies in sort of 3-dimensional space in order to demonstrate this. Let's call that the point A. Now, in order to sort of visualize this, I think it helps us to draw a kind of box around this. So let's try and picture draw a box that's kind of completely enclosing this. Alright, so can we picture that now? It's got an x, or a component in the x direction, a component in the y direction, and a component in the z direction. So its component in the x direction is this one down here. Now we could represent that as a vector. Let's just say at this stage that it's got a magnitude of a1 in that direction. Its component in the y direction is this one here. And again, we could write that as a vector. So let's say that is a distance or a magnitude of a2, and then its component in the z direction is going to be this one here, which we could write as a vector. Let's say its magnitude is a3. So in other words, we're saying that the vector A has components of a1 in the x direction, a2 in the y direction, and a3 in the z direction. Now, if we introduce for ourselves a third unit vector in the direction of the axis, so if we introduce a vector k, which is a vector of magnitude 1 in the direction of the z-axis, then we could write this also as a1i plus a2j plus a3k. So hopefully that's not too much of a sort of stretch to go there. We could also say then that the magnitude of A is equal to square of a1 plus the square of a2 plus the square of a3, which is really Pythagoras in 3 dimensions, which we've done a little bit of before in maths. Now that's one that does appear on your formula sheet. There it is there. So I just put that in there to make sure that you're clear that one's on your formula sheet. So some of these vector formulas on our formula sheet, they don't put a version in for 2-dimensional vectors. They only put it in for 3-dimensional vectors. And I guess life's not too hard, because we know if we've got a 2-dimensional vector, well, we don't have an A3 component, so we just don't have this component here, but the rule still applies for the I and J components. So the more general form, or the 3-dimensional form, is the one that appears on the formula sheet. Alright, a few more results before we finish off. And in some ways, this is where some of these results become sort of much more useful when we're working in 3-dimensional form, because life becomes a bit more complex sometimes in 3-dimensional form. Alright, so if we've got a vector joining 2 points A and B, and those have position vectors A and B, so let's go, here's our O, so we'll say that's position vector A, there's position vector B. And we wanted a vector which gives us the position of the midpoint, so M, where M is the midpoint of the line segment joining A and B. But we actually want a vector which will give us the position of O relative to the origin. So that would be a vector OM, okay, which is the position vector of M relative to the origin. Now, I don't know whether you remember this one. I won't go through how to develop it, but if you like to, you might do that just to remind yourself. But it's true always that the position vector of the midpoint will be equal to half the vector sum of A and B, where A and B are the position vectors of points A and B. Right, let's talk about a few other things to do with vectors. So firstly, parallel vectors. So if I have two vectors, A and B, and they're parallel, now obviously, don't sort of relate this back to this kind of situation here, because clearly I'm not talking about A and B. In fact, just to save the confusion there, maybe I'll actually use different. So let's say U and V here. So if two vectors U and V are parallel to each other, that means that one can always be expressed as a scalar multiple of the other. So that's where K is any real number, except of course 0. So if two vectors are parallel, then one is going to be a scalar multiple of the other, but probably, or more useful in some cases, is the converse of that result, that if U is a scalar multiple of V, then it means that U and V are parallel to each other. So in other words, if we can express U and V as scalar multiples of each other, then we've done enough to show that they are parallel. And that's something that might be useful to us in our vector proofs. Finally, before I just do a quick worked example, the idea of a unit vector. So we've got I, J, and K, which are unit vectors in particular specific directions. But if I just want the unit vector of any vector A, in other words, a vector which is in the direction of A but only has magnitude 1, well, really all I need to do is scale that down. So I'm basically going to say, let's scale the vector A down, or maybe up if it's shorter than length 1. So scale it down by its own magnitude, but still have the direction of A. Alright, so finally then, let's do a quick example. Let's convert the vector U equals negative 3 root 3I plus 3J into polar form. Alright, so polar form, I'm going to always draw for myself a little sketch of this. So let's go negative 3 root 3. Should have really drawn that. Let's do that again. Let's draw for ourselves just a little set of axes here. So negative 3 root 3 plus 3 is kind of somewhere in that quadrant there, isn't it? So let's say that length there is 3 root 3. It's in the negative direction, and that length there is 3. Now, for this, I need to find, so that angle there is actually the directional component here, and that's R. But all I'm going to do, rather than sort of complicating things with x's and y's being positive or negative, I'm just going to work in this little acute angle triangle that I've got here, and I'm just going to find that angle there, and then I know that the angle that I'm interested in is just 180. Take that. So this is my, let's call that one alpha there. So I'm going to say first of all that R is equal to the square root of 3 root 3 squared plus 3 squared, and that's going to be equal to, so the square, or the square of 3 times root 3 is 27, isn't it? Plus 3 squared, so plus 9 is 36. So that's going to simplify down to just 6. And alpha, so tan alpha is going to be equal to opposite over adjacent, which is 1 over root 3. And so therefore alpha is equal to, well, which angle has a tan value of 1 over root 3? That's 30 degrees, or pi on 6. So therefore, theta is going to be pi minus pi on 6, or 180 take away 30, and that's going to be 5 pi on 6, or 150. So therefore I could say in polar form, vector u can be written as a vector with magnitude 6 and direction of 5 pi on 6. So to just sort of confirm what I'm saying about, if you simply use the rule, let me write it over here, if you simply use the rule tan theta equals y over x, then I'd be saying tan theta equals 3 over negative 3 root 3, which is negative 1 on root 3. Now, if you sort of whack that in your calculator, well, in degrees mode anyway, that would probably give you the angle negative 30 degrees, which would suggest that this vector is in quadrant 4, because negative 30 degrees is in quadrant 4. But it's not, because tan is also negative in quadrant 2. So I think it's much easier just to always use a kind of acute triangle, whichever quadrant you happen to be in, and then express it relative to the positive horizontal direction.